It is a great pleasure for me to open and to welcome you to the International School of Astrophysics, named after the pioneering French astrophysicist Daniel Chalonge, and to this inaugural course on current topics in astro-fundamental physics, which is placed in the framework of the Galilean celebrations taking place in Europe. At the same time, I would like to welcome you to another event taking place in this same building as a part of this school, and this is the opening of the Museum Daniel Chalonge, Erice-Centro de la Ciencia. All of you, your families, and accompanying persons are kindly invited to visit the museum and the exhibition. Thank you very much for coming. I hope you will have a fruitful and enjoyable stay in Erice and during this school. As it can be seen from our timetable, time is precious here. Let us start. And it is a great honor and great pleasure for this school and for myself to have here Professor Chandrasekhar from University of Chicago, who gave the opening lecture of the school, Daniel Chalonge and the problem of the abundance of the hydrogen, and the second part, the harmonious blending between the mathematical structure and the physical content of the general theory of relativity. Let us welcome Professor Chandrasekhar.
Ladies and gentlemen, it is a great privilege for me to give this opening address at this first course in the International School of Physics dedicated to Daniel Chalonge. Daniel Chalonge is a scientist whom I have admired greatly and whose friendship I have cherished. And it's a pleasure for me to pay my homage to him today by recalling some very essential and crucial contributions he made to resolving one of the great problems of astrophysics of today, the enormous abundance of hydrogen in the universe, which all of us take for granted. It is now almost accepted without doubt that by numbers, the ratio of hydrogen atoms to helium atoms and all the others is 20,000 to 4,500 to 8. In the theory of stellar atmospheres during the 30s and 40s, hydrogen and helium were lumped together under the one pseudonym H, because both these atoms were mostly unionized and were in the neutral form. So consequently, the ratio of H like sodium, potassium, iron, and other elements which are mostly ionized. And the ratio of the hydrogen, by which one means hydrogen plus helium, and to the metals, by which one means all the other elements, by numbers, are in the ratio 4,000 to 1. And those of us today who accept this enormous abundance of hydrogen, almost without doubt, may not be aware that during the 20s and 30s, the abundance of hydrogen was a matter of great controversy and intense debate. And the debate was between the giants of those times. Henry Norris Russell championing a ratio 1,000 to 1, while Albrecht Wunzel championing the ratio some 14 to 50 to 1, an enormous difference. Now, the surprising thing about this difference was that the physical premise underlying both these directions was the same. Both Russell, Wunzel, and all the others at that time assumed that the principal source of absorption in the atmospheres of stars derived from hydrogen and from all the other elements which I have called metals. And of course, the absorption by hydrogen, the continuous absorption by hydrogen, comes from the continuum beyond the head of the bomb series and the head of the Partian series, while the absorption by the metals are due to the absorption in the continuum of the various other elements. And the assumptions were the same, both in Russell's and Wunzel's. I'm using the word Russell and Wunzel as the protagonists of the two groups. And Russell's method was to look at the intensities of the various lines, and in particular the intensities of molecular bands, the hydrides, and he came to the conclusion that the ratio of hydrogen to metals must be 1,000 to 1. On the other hand, Wunzel, who based his deductions on the observations of Chalonge and Barbier on the discontinuity at the head of the bomber series, and about which I shall say a little more presently, came to the conclusion it was about 50 to 1. Now, how does it happen that there are two conclusions drawn on the same premise gave such very different answers? I shall come to that in a moment, but the point is that there is, in addition to the problems that I have mentioned, another aspect of the same problem which was also crucial, and that is the relation between the color and the effective temperatures of stars, which essentially give you some idea about the source of the continuous absorption in the stellar atmospheres, and more particularly the source of continuous absorption in the solar atmosphere. Now, I have mentioned three things connected with the problem of hydrogen: the discontinuity at the head of the bomber series, the relation between the color and the effective temperatures of stars, and the source of opacity in the solar atmosphere. In all these three areas, Daniel Chalonge and his collaborators, in particular Barbier and others, made essential, if not the important contributions. On this account, let me go back a little and recall that in 1931, Chalonge and Barbier established on Jungfrau Joch an observatory which was at an altitude of 3,500 meters. The high altitude of this observatory made possible the study of ultraviolet stellar spectroscopy, and Chalonge initiated a carefully planned program to study the discontinuity at the head of the Balmer series. I shall indicate in a moment what that is, and also about the slope of the continuous spectrum on either side of the discontinuity. And by 1939, Chalonge and Barbier had assembled the material of some 200 stars on this matter. Perhaps I'll begin by showing an example of the kind of phenomenon the moment discontinuity is. You have a pointer here. You see here in the spectrum the series of the Balmer lines coming. Yes, thank you. You see the series of Balmer lines coming to a head at this point, and you see the rather sharp discontinuity there, and that is a normal star. On the other hand, if you take this star here, you see three differences. This is a supergiant, and that is a star with the extended atmosphere. And the problem is to determine the slope of the spectrum on this side and on that side, and the measure of that discontinuity. And these were extraordinarily beautiful work at that time. And I give you another example, which is a very famous one. And in fact, I noticed that it is reproduced in the brochure for this meeting. It is the largest discontinuity that Chalonge and Barbier observed in the case of Vega, where you see the various hydrogen lines and an enormous discontinuity. Now, you can ask, why is the discontinuity at the head of the Balmer series so essential for the problem of the abundance of hydrogen? Perhaps one can see by this diagram, which is an idealized version. You have here the intensity of the star, and this is against one over the wavelength. So this is the short wavelength side. And as you come to the head of the Balmer series, there is a discontinuity, and the slope AB and the slope DF, and the discontinuity by those quantities which Chalonge and Barbier measured. Now, why is it so important? The reason is, if you have that only radiation to the short wavelength side of the head of the Balmer series can ionize the hydrogen atom in the second quantum state. And the cross-section for absorption beyond the head of the Balmer series is very high relative to the background. And on the other side, the essential absorption is due to sources of opacity besides hydrogen. Consequently, in the absence of any other source of absorption, the discontinuity is directly a measure of the abundance of hydrogen and the abundance of all the other elements which produce the absorption in the background. And Michel was right in saying that the deduction of the abundance of hydrogen from the discontinuity is the clearest, simplest way in which one can do it. And as I explained, he found a value of some 50 to 1, whereas Russell found a value of 1,000. The question arose, what is the resolution of this discrepancy? But before going to that, perhaps I will show you the kind of observations which were later to become extremely important. Here, for example, is the variation of the discontinuity at the head of the Balmer series observed by Chalonge and Barbier as a function of the spectral time, which is here. And as you see, the discontinuity increases from high temperature stars, and this is the lower stars from G to A. discontinuity increases. And precisely the fact that it increases in this domain is the reason for Unsel's derivation of the low abundance. Now, this is the other set of measurements which give you the variation of this spectral type, and these are the color temperatures, and the question is, how does the ratio, the relation between the color temperature and effective temperature take place? I've summarized very briefly the enormous amount of work which Chalonge and Barnier did during the 30s. But and of course the question is, how does one resolve this problem? The point I want to emphasize here is that the solution to the problem of the hydrogen abundance did not come directly into the interpretation of these observations. It rather came from a related one, and that is the source of absorption in the solar atmosphere. And on this subject also, Chalonge and Kubanov made fundamental contributions. Now, what is the solution of these two problems are really solving the same problem of hydrogen abundance. And the solution to it was provided in 1938 by a suggestion of enormous perception by Rupert Miller, who pointed out that one may expect in the atmospheres of these stars a sufficient number of negative ions of hydrogen, that is, hydrogen to which an extra electron is added. I shall come to this identification a little later, but let me explain why this problem was equally essential as the problem of the discontinuity at the head of the bomber cities. What one is interested in is that the solar atmosphere in particular has a variation in the continuous spectrum. Now, this is not a black body spectrum, and the question is, what is the origin of the variation of the difference between the observed distribution in wavelength of the continuous spectrum of the sun with respect to a black body? And the basic observations which one used were those of Abbott and Fang and Aldrich, who for nearly 20 years had observed the intensity distribution with wavelength of the integrated solar radiation, the distribution with wavelength of the radiation coming from the center of the solar disk, and what is even more important, the variation of this intensity as one goes across the solar disk. That is to say, the darkening. That is, if you take a particular wavelength and measure its intensity from the center to the disk as you see the sun, there is a variation, and this is called the darkening at the limit. And one wanted to find the variation of this darkening as a function of the wavelength. And the measurements of Abbott and Fang were reduced here. For example, this is the measurements of Abbott and Fang, and the other points are observations of others. And these were all reduced to a standard system by Minard. And of course, when one looks at the continuous spectrum, in the case of the sun, one doesn't see complete because it is the absorption lines which crowd it out, and one had to make corrections for that. And Mouette, one of Minard's students, showed how the observed spectrum here has to be corrected from the crowding, and that is now the distribution of in wavelength of the continuous spectrum of the sun, allowing for the blackening effect and absorption lines. The question arises, why is this darkening so essential to determining the abundance of hydrogen in particular? Now the answer is the following. When we observe the darkening, here's the solar disk, and you see the radiation coming from the center and from at a point away from the center and from the edge, that is the limb. And one observes the variation in intensity as you test to the limb. You can see from this diagram that the darkening of the solar disk essentially is equivalent to determining the variation of the intensity as a function of the angle of emergence. For example, if you take this radiation, this is coming normally from the center, normally with respect to the surface, whereas this radiation here, which you see at that point, is at an angle to the normal, so that the radiation here is the same as the radiation coming from that angle. In other words, the variation of intensity on the solar disk is a measure of the variation of is the angular dependence of the radiation as it emerges from the center of the sun. In other words, the darkening one observes is essentially the variation in intensity with angle. Now, why does the variation arise? Because the light which you see, say at normal to the surface, is an average of what you see at all depths. The radiation from the deeper layers is obscured by the fog. And so the radiation you see normally is the weighted average of a radiation at some lower level. On the other hand, when you see at an angle, because of the slanting path, the representative depth of the radiation is higher. You see, that distance is about the same as that distance. And consequently, the radiation coming at an angle is characteristic of a level in the atmosphere which is higher than the one radiation which comes towards the center. And if there is a temperature dependence, temperature variation in the atmosphere, then it is natural that the radiation at the center is characteristic of a higher temperature than the radiation which comes at an angle, which is at the temperature of a layer higher up and therefore of a lower temperature. In other words, the darkening must result in some way from the temperature dependence in the outer layers of the sun. But in addition to that, suppose you consider the radiation coming from the center. Now, it is true that the total radiation is the average at that point. But suppose you consider two wavelengths. One wavelength at which the absorption is high, and the other wavelength in which the absorption is low. Clearly, the radiation at which the absorption is higher will come from a level which is higher up than the radiation which has low absorption, which will come from the deeper layers. In other words, the radiation at a wavelength where the absorption is high is characteristic of a lower temperature than the radiation which comes which comes from a smaller absorption coefficient, which is of a higher temperature. So consequently, on the other hand, when you see the radiation coming from the limb of the sun over here, then no matter what the absorption is, you always see the surface layers. So consequently, in a region of the spectrum where the absorption is high, you see essentially only the surface layers at all angles. On the other hand, when the absorption is low, at the center you see deep layers, at the surface you see at the deep layers, and at the limb you see the surface layers, and therefore the darkening is greater. It is now clear that by an analysis of the darkening in different wavelengths, combined with a knowledge of the temperature distribution, you ought to be able to derive the variation with wavelength of the continuous absorption in the solar atmosphere. The theory underlying this was worked out by E. A. Mill in the early 20s, and a refined analysis of this kind was made by Mouette, and this is what he found. The absorption coefficient, this is 4,000 to 5,000. The absorption coefficient decreases here up to 4,000, increases rapidly up to about 9,000 angstroms, and decreases to 18,000 angstroms and rises again. This variation of absorption coefficient is derived so simply that one had to conclude that a new constitution of the solar atmosphere was involved. And as I pointed out, the solution to this problem was made by Wild, who said it must be due to the negative ion of hydrogen. The negative ion of hydrogen consists of a hydrogen atom plus an electron. And the stability of this atom had been established by Vega and Erice in 1930 on the basis of a variational calculation which determines the ground state of atoms. And the electron affinity of the binding was about 3/4 of a volt. Now, the fact that the electron affinity is 3/4 of a volt means that there will be absorption due to the negative ion of hydrogen all the way from 18,000 angstroms into the visible. And that you have a new source of absorption. And by rough calculations, it was possible to show that the presence of the negative ion of hydrogen will resolve the discrepancy between Utzow's and Russell's evaluation of the abundance of hydrogen. But before one could be certain of it, one had to make a precise calculation of the coefficient of continuous absorption of H minus. This happened to be a fairly difficult problem because the wave function of H minus was known only by a variational calculation, and to compute the cross-section is not so easy because the negative ion of hydrogen is a big atom. Its radius is about 6 times the radius of the hydrogen atom. And so in order to compute the cross-section, you must know the wave function with sufficient precision at large distances. And this is not an easy problem, and you can see here the effort taken. For example, this is the kind of variation which had been deduced by Massey, Bates and others in 1939, whereas by 1946 it had been improved to this value. And you can see that the total cross-section has a maximum at 9,000 angstroms and increases with a sharp minimum. So that at this point it became clear that the identification of H minus can be made precisely. And at this point, it is at this stage that Chalonge and Nobel did their splendid calculations. And what they did was the following. Suppose you take a layer in the sun, say at 6,500 degrees. It is deeper, at a deep level. You can ask, what is the continuous absorption of the solar atmosphere of the layers above the temperature 6,500 degrees? It is 6,500 degrees and it is at a certain depth. And you have a certain amount of layer above that. What is the absorption coefficient of that layer as a function of the wavelength? And you do that for different assigned temperatures. For example, this is a variation of layers above the 5,500 degrees. That is 6,000, 6,500. These are the deduced absorption. These full-line curves are the curves deduced by Chalonge. And the dotted curves are those computed from the theoretical cross-sections. And with this analysis of Chalonge, there can be no doubt that the negative ion of hydrogen is present, is of some opacity, and as one could. And once the absorption cross-sections were sufficiently well known, it is not difficult to go back and reinterpret the observations of Chalonge and Barbier on the Balmer discontinuity, the relation between the color and the effective temperatures, and show once and for all that the abundance of hydrogen is exactly what it is. Now, I wish I had more time to go into the details of this thing. It's a very beautiful work, but I did want to take this occasion to emphasize that many of the crucial aspects which resulted in solving this fundamental problem of astronomy were provided with Chalonge, and I'm glad that on this occasion I could recall for you the very important role he played in this subject. Thank you. I'm afraid I must change from my interests of my youth to the interests of an old man, because the subject which I talked about was in the early 40s, and I was greatly interested in it. That was the time I got to know Daniel Chalonge and formed his friendship. But today, my interests, since that time, my interests have changed very far, and I want to talk about an entirely different topic, namely the topic which has been announced as the harmonious blending of the mathematical content, mathematical structure, and the physical content of general relativity. When one has a subject announced with that general title, one would normally think that the subject, that the speaker is going to talk in a large, soft, vague way about matters which are philosophical, quote unquote, and therefore perhaps not with much substance. Of course, I could, if I like, talk about the subject in a largely philosophical way. But I thought it would be more appropriate if I made my comments concrete by taking two problems which at one point look very disparate in physical aspects, but nevertheless have a common mathematical structure which provides different physical relations and so on. And I want to discuss two specific problems which are related, which in the first instance look different from a physical point of view, but later appear as having a common mathematical structure. And when you proceed further with that mathematical structure, you obtain either common physical backgrounds or different mathematical backgrounds as it may be. Well, I'm perhaps not very clear in what I say, but I hope it will become clear as I go along. The two problems, the two physical objects I want to consider are the black hole on the one hand, and the short-shell black hole in particular, and spherical stars. Now, one might say that a black hole, as we know, has an entirely different physical meaning in the sense that the short-shell black hole, for example, divides ordinary space into two regions which are incommunicable, and the boundary between these two regions is the horizon, and further that anything which crosses the horizon is lost forever. Whereas if you take a star, it is a spherical distribution of matter, and the physics which is put in is that the energy momentum tensor which governs this distribution of mass is that of a perfect fluid, in which the energy momentum tensor is epsilon plus p times ui uj, where ui and uj are the components of the flow velocity, minus gij times p. It doesn't matter what it is the energy momentum tensor of a fluid. Now, of course, a star is an object in which there is no horizon, and the center is the center of the star is a perfectly normal place, and the question is, these two objects look in the first instance as entirely disparate. On the other hand, if you look at these two objects from the point of view of general relativity, their space-time are essentially the same, because the space-time of which one is ds squared the space-time is a product of S2 cross U2, by which I mean simply the metric is a product, is a chronic product of a part which is indefinite and a part which is essentially the surface of a sphere. That is, ds squared will be equal to, say, e to the 2 nu dt squared minus e to the 2 nu to dr squared, which is the indefinite part u2, minus d omega squared, which is r squared d theta squared plus r squared sine squared theta d phi squared. And the metric of both the star and the black hole are of the same kind. So the space-time is fairly symmetric and has very nearly the same form. On the other hand, we know also that the black hole represents the solution of a vacuum, whereas a star represents a solution of the Einstein equations for a fluid source. And consequently, the two are in one sense very different. As I said, a black hole is one for which you have a horizon, and a star is a perfectly simple object with no horizons, no singularities. However, one should remember that the space-time outside a star is a vacuum space-time, and it is governed by the same equations as the space-time of a Schwarzschild black hole. And therefore, the two are not that different after all. And now, so you see that the two things have a certain mathematical background, and while they are described different physical objects, they have a certain common feature, namely the outside of a star is essentially the same as the outside of a black hole. But then, what are the problems which one wants to deal with in the case of a black hole and in the case of a star? In the case of a black hole, the problem one is primarily interested in is how does a black hole react to external gravitational waves? If you have gravitational waves instead of the black hole, then a certain amount will be reflected. A certain amount will be absorbed, that is lost, will cross the horizon and lost forever. What is the ratio of the reflection to the transmission coefficient? That is a primary question. There are other questions one can ask, but this is one of the important questions connected to black holes. But what about a star? The fundamental problem of a star is how does it react to external perturbations? That is, in general, a star, if it is perturbed in some way, will oscillate non-radial. And therefore, one is interested in the non-radial oscillations of stars. And of course, in the Newtonian theory, the subject of non-radial oscillations have been studied to great extent. But on the other hand, stated that way, the problem of a black hole and the problem of a star may look very different. But look at it this way. Perhaps at this point I should say that much of what I'm going to say about stars today is the result of some work which done in the past year or two with Valeria Ferrari of Rome, a very distinguished relativist. Now, as I said, let us look at the non-radial oscillations of a star from a different way. We know that an oscillating star, particularly in modes which are quadrupole and higher, will radiate energy, will radiate gravitational waves. Consequently, instead of thinking non-radial oscillations as being produced by arbitrary perturbations, you can think of the oscillations as being induced by the incidence of gravitational waves. And if you consider, in other words then, the natural way in general relativity to think of oscillations of stars is to see how they scatter incident gravitational waves. And you see, when you state the problem this way, the problem of a star is very nearly the problem of a black hole. In both cases, you want to study the scattering problem. And actually when you go into the scattering problem, you realize that the problems are even mathematically even more alike. For example, if you take a star or a black hole, they are spherically symmetric. And you want to consider how they react to external gravitational waves. Now, there is no loss of generality in supposing that the star, during its oscillations, is axis-symmetric towards one axis. This does not involve any loss of generality, but I won't stop to explain it. It must be evident in general terms that for a spherical object there is no loss of generality, assuming that departures from sphericity are axis-symmetric. So in both cases you can make this idealization. But what is even more important is that these oscillations are essentially of two kinds, which I call axial and polar. Axial perturbations are those in which, for example, if you take a star and you take what I call polar perturbations, the star changes its form periodically. But the form changes by being ellipsoidal, oblate to prolate, and so on. And the axis remains the same because we have assumed it is axis-symmetric, and as I have explained, there is no loss of generality. So the star essentially executes what one might call bleeding oscillations, goes up and down and goes flat. And the other kind of oscillation is polar, is axial oscillations, in which you induce a certain amount of rotation in the object, so that the oscillations which I call polar and the oscillations which I call axial are of opposite magnitude. And this division can be made in both cases. And what is even more striking is that the equations governing these things are very nearly the same. They are not very clear. It doesn't matter to look at the equations. The main point is, on the top here, I have the equations which govern the polar oscillations of black holes. On the bottom, I have the polar oscillations of a star. You see, they're very line for line, they're the same. The only difference is, in one case, we are dealing with homogeneous equations, in the other case, inhomogeneous terms. So there is very little difference. And in fact, those are the general terms, but when you separate the harmonics, the equations become even more similar. You see, there is zero, and here it is not zero. Apart from that one difference, the equations are the same. For example, this equation here is exactly the same as that. In other words, the mathematical structure of the problem dealing with the oscillations of stars and the mathematical structure dealing with the reflection and transmission of gravitational waves of black holes are very nearly the same. And in fact, the analogy is even greater because you would not expect it. Because when you look at a star and when you have gravitational waves incident on it, they will induce motions inside it. And the hydrodynamic equation will come in. But the remarkable fact is that when you deal with the theory of oscillations of stars in a manner which you have learned how to deal with the equations of black holes, you can eliminate all the hydrodynamic variables. And what you are left is simply the way in which a spherically symmetric space-time will scatter gravitational waves, the scattering taking place because of the potential associated with the gravity of space-time. So up to this point, they are the same. But then, so in other words, the two problems started with two entirely different physical objects. They have the same mathematical basis in the general theory of relativity. The problems you wish to consider are different, but when formulated suitably, the mathematical problems become identical. But of course the physical problems are the same, are different, and therefore this difference must manifest itself when you pursue the theory. Let me take the theory of black holes. facts about the way in which radiation is scattered with the functional black hole is that when you consider polar oscillations or axial, that is, you can consider polar gravitational waves incident in the star, and you can consider axial gravitational waves incident in the star. You can treat these two problems separately, and what happened? What is the result of the analysis? You find that in both cases, both polar and axial are governed by a one-dimensional Rayleigh equation of exactly the same form. And moreover, the potential which appears here, as you see, is a very complicated one, whereas the potential here is very simple. Well, and the remarkable fact which you now see is the following. Even though the potentials which govern the scattering of axial waves and polar waves, they are so different, nevertheless, they are isospectral. That is to say, the reflection coefficient and the transmission coefficient for both axial and polar waves are exactly the same. Now, that is very remarkable. On the other hand, immediately it suggests a problem. Some of you may be familiar with the theory of the solitones, and in particular the theory of Korteweg-de waves. And there one is accustomed to thinking of potentials whose spectral characteristics are independent of time. But here you have two discrete situations, and they have the same spectral character. And therefore the theory of black holes must be related in some way with the theory of the solitones. That is one thing. And the second question is, how does this equality of the reflection transmission arise? And they arise, perhaps before I go into it, I forgot to point out one important thing, namely the potentials which which are characteristic, which appear in the two equations. In the two equations are these. And the important point I want to draw attention is that the potential attain a certain maximum at a radius about thrice the Schwarzschild radius. And that is true for both the axial and the polar waves. Now, to return to the other question, you see these are the other kinds, and you can see again that the potential attains a maximum. 2, 3, and 4 correspond to the various spherical harmonics. Now, why do they arise? It arises because even though the two potentials are very, very different, they are related. And in fact, one shows that the two potentials which appear in this problem, say the V plus for the polar, V minus for the axial, they can be derived from this single equation with Vega having a plus or minus sign and F exactly the same. In other words, if you substitute in this expression F this expression and choose Vega plus M or minus M6M, they are the two potentials. And the question is, why again? How does it happen that when you treat a black hole, you consider two entirely physically distinct problems? Incident gravitational waves and incident axial waves, and they are both characterized by a potential which can be changed one into the other by the simple transformation. What is the origin of that? Now, the origin of that goes deep into what one might call the spin-off character of space-time. I can't go into that, but Newman and Penrose developed in the late 60s a way of looking at space-time in which you set up at each point a spinner, in fact 2 spinners, and this description of space-time in terms of spinners is fundamental for the theory of black holes. And if you look at the problem of reflection and transmission from this higher point of view, then one finds that there's only one equation which governs both of them. And in fact, the equation which you derive from the Newman-Penrose formalism does not distinguish axial and polar waves. And therefore, you are confronted with a transformation theory, you start from the number of spins, you go into the polar equations, and you go into the action equations, you can go from one to the other, and consequently you should go that way too. And that is the origin. So what we have seen here is that by looking at the mathematical solution of the reflection of waves, you find that the mathematical theory leads you to a theory of transformation based upon the spinorial character of space-time, and on the other side, to the theory of solitons. Now, let us look at it. Now, let us look at the structure of stars. Now, in the case of stars, you want to consider the scattering of waves. And the scattering of waves is essentially one in which you have a star and you have radiation incident on it, and you come back. And normally, the problem one is interested in the case of a star, as I said before, is that a star, when it oscillates, it radiates energy. And therefore, the solution you are particularly interested in is a star which is oscillating and radiating in such a way that you have radiation which is only going outwards, that is purely outgoing radiation. Now, this phenomenon which you see here is not very different from what one encounters in atomic and nuclear physics. You take a radioactive atom. Now, what does a radioactive atom do? It has an alpha particle in the interior, and it stays in the interior for quite a long time, but it decays. And so, in other words, the alpha particle inside the nucleus executes oscillations back and forth, and once in a while it escapes. And that's exactly what happens to a star. So consequently, the non-radial oscillations of the star is related to the problem of what one calls in atomic and nuclear physics quasi-stationary states. That is, energy analysis for which the system can exist not as exact solutions of the theoretical equation, but approximate solutions, an approximately stationary state, which lives for a very long time, but eventually decays by tunneling. Now, that's exactly what happens to the star. So, consequently, the theory of non-radial oscillations in general relativity leads naturally to the theory in quantum theory which deals with quasi-stationary states. And perhaps the best way to explain it, and at the same time point out the enormous difference in content between Newtonian theory and general relativity. Of course, in many, many cases, the aspects which were obtained from general relativity have similar analogues. In fact, sometimes even the same, very nearly the same quantitative results, whether you do it in general relativity or in Newtonian theory. But there are situations where the two are very different. Now, let me state it in the following way. I said that in discussing the oscillations of stars, you can think of it as being induced by incident gravitational waves. The incident gravitational waves can either be of a polar kind or of an axial kind. Now, the point is, of an axial kind oscillation simply corresponds to imparting a rotation to a spherical object. In the Newtonian theory, you cannot do that. And indeed, even in relativity, you cannot do that. Because to induce an angular momentum in a spherical object means that you have to violate the conservation of angular momentum. And so consequently, in the Newtonian theory, when you deal with non-radial oscillation, there are no such things as axial oscillations. In general relativity, even though axial oscillations do not exist, by which one means that the incidence of axial waves will not induce any motions in the system, there is nothing which prevents it being scattered. And so the incident gravitational waves can be scattered. of course you can say, well, it's scattering wave and therefore not of much significance. Well, let me emphasize the problem this way. And this again brings you back to the common mathematical structure of actual waves for black holes and actual waves for stars. You see, when you look at the actual perturbations of a star, then, that is to say, what happens on a star, you have a star and you have incident actual waves. Then, it does not induce any motions. But as I said, there is nothing which prevents it from being scattered. And when it is scattered by the curvature of space-time, acting as a potential. And in fact, one can show that if you introduce this variable R star, then the actual oscillations are governed by a one-dimensional potential equation, exactly as the actual oscillations of a black hole. However, this potential, of course, does not go to the horizon and end there, because that is where the black hole has to end. There is nothing beyond the horizon which anybody outside can see. But here, R goes to 0, and in fact this variable degenerates into R, the ordinary radial distance, when R goes to 0, and it also degenerates to the radial distance R when you go to infinity. So it is that radius, you see. And this is the potential. And clearly, also, when you take this, when you go outside the star, epsilon will appear 0, and it becomes the standard black hole equation. So consequently, you have here a problem where you have a potential scattering. And normally, if you ask a potential scattering, what is the potential? Well, I have here a graph of the potential for a star which is very nearly a neutron star. You see, the potential, this is the boundary of the star, it's the black hole and the star have exactly the same potential. The potential inside the star goes up, it goes to infinity because of the centrifugal potential. But whereas for a black hole, you see, it ends at the horizon, and it has a maximum, as I pointed out. So, for a star like this, an incident actual wave would simply be reflected in a standard way, like elastic scattering. However, this picture indicates, what if the star has a radius less than the maximum value here? You can ask that. And if you did that, what is the situation? Actually, this can happen for very, very compact stars. For example, I have here a series of potentials for stars with radius, this is twice 1.3 Schwarzschild radius, 1.4, 1.3, 1.2, 1.15, 1.14, 1.13. The minimum radius is 2.25, 1.25. But now you see, here you take a potential like this, a star with such a small radius. The potential increases and decreases. Now, that is exactly the kind of situation where you can have a quasi-stationary state. The potential is not very different from that of a potential of a nucleus which disintegrates into an alpha particle. Now, just as an alpha particle has a stationary state inside, you can have a stationary state here, and it will decay. In other words, an actual oscillation, an actual wave, can produce in a star oscillations of a kind in which it oscillates with the real frequency and radiates energy at the same time. Phenomena which have altogether no analogues in the Newtonian theory. In the Newtonian theory, you do not have any oscillations period. But in general relativity, it is not simply a triviality that you have elastic scattering, but you can have a scattering in which the star oscillates with a real frequency and goes away. Now, the next question, of course, is what happens to poor oscillations? Well, that is a much more difficult problem. But there you have the relation with potential scattering is not as great. But nevertheless, you can compare the polar oscillations of a star with something which you are acquainted in nuclear physics. One knows that if you have a high energy proton or neutron incident in the nucleus, then according to the conventional picture, the proton or neutron goes inside the nucleus, a quasi-stationary state is formed, and then it decays. The same thing happens. But I notice people are conferring about the fact that I'm transgressing my time. I'm keeping my time. I'm supposed to go to 10:30, and I still a few minutes here. So I may just point out a few things at this point. When you consider the non-radial oscillations of the star at a formal level, oscillations of the star at a formal level, and indeed more than a formal level, they're the same as the theory of a black hole. On the other hand, what are the problems, physical problems, which arise when you look at it as physical problems? In the case of the star, the physical problems are the resonant scattering, that is to say, scattering at certain frequencies where the cross-section is high. And there is another aspect of the problem which I haven't touched upon. Namely, there is one extremely important aspect of this problem. Namely, if you have a star and it radiates energy, you can ask, how does the gravitational wave, the flux of gravitational wave increase when you go from the center to the outside? A problem which has not been confronted till very recently. And Valeria and I have shown that by appealing to the so-called Regé theory of poles, the Regé scattering, in which the angular momentum is considered as complex, we are able to show that using the Regé theory, we can actually determine the flow of radiation through a star. For example, here, it gives you precisely how the radiation flux goes from the interior to the outside and then settles down to the value. The point which I want to say then is that the fact that the two problems are physically different implies that in the case of scattering by a star, the problems which arise are physical. The Bright-Wigner scattering formula for resonant scattering, the Regé theory of poles, the existence of quasi-stationary state, and all that. And to emphasize what I've been saying, let me take this picture here. You see, you start with a black hole, and with Faraday stars. They both represent static space-times, called a product of S2. One deals with the vacuum, the other sees the fluid source, we are interested in non-radial oscillations, reflection of gravitational waves. Both lead to scattering problems, which are physical, and mathematically they give rise to similar equations, similar decompositions, but then this goes into isospectral theory and solar theory, which are mathematical theories, whereas here you go into resonant scattering, Bright-Wigner formula, and the Regé theory. What I want to say is that here are two problems in which the mathematics and physics have a confluence, they bifurcate, they have a confluence again, and it is characteristic of general relativity. This kind of relation exists. There are other topics which I have talked about, namely, for example, the theory of black holes in general, and the theory of colliding waves. And there again, one can show that while the physical problems are different, the mathematical problems have a confluence, and the physical problems problems which emerge are different again. So I hope that I've tried to show in the time being that in the geography of relativity, the problem of exploring the physical content is not very different from exploring its mathematical structure. The two happen to be the same. Thank you.
In the work of Chalonge also a similar study about the oxygen negative ion. Could you comment about that? Because I think that at that time also was important to...
it was, but I have not followed the literature really greatly, but my impression was that the application to negative ions of hydrogen, oxygen, did not turn out to be well. That's what, I mean, I know that Bill and I were interested in it at one time, but we later gave it up. But of course, you realize that I have not tried to describe Chalonge's life's work, which is extensive, but I did want to point out to an audience, which are polycosmologists, who conceivably had never even heard of this controversy which existed at one time. And to the resolution of it, Chalonge played an extremely important part, if not the important part.
Concerning, if I can do a comment concerning the second part of your very interesting talk, I am wondered about, of course, there is all this beautiful, as you stressed, analogy between the scattering of perturbations by stars and by black holes. But if you look not just at the elastic scattering or the reflection coefficient, but at the absorption cross-section of a black hole and another object of that kind of stuff, I think that there you can see the very difference between these two objects. In the absorption cross-section, the peculiarity of having a horizon or a singularity by a black hole should appear.
Well, I'm sure you're right, but I was conscious, of course, the reflection coefficient plus the transmission coefficient has to be equal to 1. And of course, that comes from the nature of one-dimensional scattering. And the point I wanted to emphasize was that the reflection coefficient for action rays and the reflection coefficient for polar rays are exactly the same. And so the point I wanted to emphasize was that. But of course, the difference comes in a variety of ways. For example, if you look at the quasi-normal forms, and they have imaginary part, which is quite large compared to the stars. So there are a number of differences, but clearly, with the time available, I have to concentrate on a few things.
Thank you.
One question?
Yes, please.
So can you elaborate more on what does it mean that gravitational wave is scattered by, for example, like if charge, if there is electromagnetic wave?
I'm sorry, what is the question?
When you said there's a scattering, the gravitational wave is scattering by the stars.
Well, it is no different than...
Yeah, so more like a pumping wave.
There's no difference between the scattering of in fact the theories, both physical and mathematical, are the same. But you see, one might think that in one case you are dealing with microscopic problems, in the other case with macroscopic. But the point one should realize is that, but I don't want to go into these philosophical things, but fundamentally, in quantum theory, the transformation of one kind of energy to another takes place because of the different channels which are involved. But, for example, in relativity, gravitational waves can be converted into electromagnetic waves. If you have a space-time in which the gravitational perturbations through the interaction with the source perturbs the electromagnetic part. So the non-linear character of general theory of relativity implies that you can have scattering of gravitational waves with the curvature of space-time.
Okay, so you mean
exactly the same as the scattering of electrons and protons by
okay, I understand. My question is, if there is a photon being absorbed by a charged particle with the microscopic, we can display. Photon is being absorbed by a particle and being emitted. Now in the case of a gravitational wave, it comes into the star. Does it mean that the gravitational wave is absorbed into the star and the star begins to oscillate and re-emit gravity?
No.
Does it mean?
No, I don't understand the question. But the point is, if the energy is lost, it is lost.
Oh, there's no I'm just asking a microscopic exaggeration.
No.
What does it mean?
But an important point which I want to say is, I am dealing with a classical theory. And the framework of the classical theory, there is no the non-linearity of the theory by virtue of the curvature of space-time, which enables the perturbation of the space-time to induce gravitational waves on the one hand and produce fluid motions on the other, is ultimately the cause of this. So, in the case of general relativity, the interaction between gravitational waves and fluids arrives via the intermediary of the space-time. Because the space-time is, that is, you take a space-time, you perturb it. And the perturbation of the space-time is first of all reflected in the emission of absorption of gravitational waves. But the space-time, being coupled with the source, changes the source. And that corresponds to the fluid motion. So, in discussing these transformations in general relativity, one must remember that even though the words used are the same, the mathematical theory is also commonly the same. The underlying cause of it is a non-linearity of the theory in which the perturbation of the space-time is a fundamental question. But perhaps we should discuss it.
From Président de la République française and Institut d'Astrophysique de Paris, who will give a lecture on primordial nucleosynthesis.
The mathematical theory is also commonly the same. The underlying cause of it is a non-linearity of the theory in which the perturbation of the space-time is a fundamental question. But perhaps we should discuss it.
from Président de la République française and Institut d'Astrophysique de Paris, who will give a lecture on primordial nucleosynthesis.
To have been invited by Norma, Sanchez and Antonino Zikiki for this school devoted to the work and the memory of the Chalonge, who was maybe one of the basic figures of the Institut d'Astrophysique de Paris. I had the chance to be the director for some time, and what I would like to do during this hour is not only to cover a quite important topic, which is maybe fairly well known by some of you, since in this room, not only myself, but people like Mike Turner, and many others have played some role, and of course the Cayrels by working on the lithium problem. But what I would like to show is that Big Bang nucleosynthesis is a problem where the pure astronomical work, which has been initiated by Chalonge, play a very important role not only to solve this problem, but also to give some constraint on very different aspects like particle physics aspects and even nuclear physics aspects. So I have a default. Normally 1 hour is never enough for me, 2 hours never also. So instead of, I will start to show to you what is the points I would like to cover if I am good enough to stick on my time. So, of Big Bang nucleosynthesis, namely the nucleosynthesis of the lightest element, deuterium, helium-3, helium-4, and lithium-7, may be one of the main arguments in favor of a very hot universe at some time and the so-called Big Bang theory. As you know, Big Bang theory is a question from time to time and rightfully. And as you know, what I'm going to show to you is given Big Bang nucleosynthesis simple schemes. I will try to convince to you that they are maybe the preferable theories now. The simplest is the preferable, but also it has to be questioned, and especially on astronomical grounds. So, let me start by a few general remarks concerning the relationship between this nucleosynthesis and the Big Bang theory. And tomorrow you will have a coverage of the present situation regarding the black body radiation, which is also a very important aspect of this question. Some other colleagues will cover the problems related to distribution of galaxies. I will touch upon the possible nature of the so-called dark matter, and you will have also a lot of contribution on that.
Showing the general relativity as foundation for this calculation. I think it would be fair to say that actually what we needed is Majorana's theory, because general relativity, modern cosmology must be relativistic in general, but for nuclear, primordial nuclear synthesis, the only what we need is the Majorana theory. What we really need is a rate of dependence and of density such things. No, it is an important point. And,
I agree entirely with your historical point of view, which is true that I should have not mentioned the Gamow, of course, and who was the first to try, but he forgotten the mass 8, 5, and 8, and he would have liked to have the nucleosynthesis done, all the nucleosynthesis is done during this primordial phases. But on the other aspect, I could not say anything about the relativistic particles, namely the constraint on the neutrino numbers comes from the fact that they are really relativistic, and that I cannot know under Newtonian theory.
There are different means of what relativistic. In terms of special relativity, there is no doubt about this, but they are discussing general relativity and general relativity. Whether it's good or bad, it has no relevance to this matter.
That was a beautiful talk, John. And if I may, I'd like to make just a couple of very brief comments. First of all, I agree about the narrowing range of parameters. And of course, if I may be so bold as to say, that's usually a hallmark or a signal of the fact that the solution is near. Right? Because ultimately there should just be one parameter. So I speak as an optimist about this.
Yes, you could. As I said, I have tried to be as optimistic as I can.
And I wanted to comment, I too, because I'm a defender of Big Bang nuclear synthesis, am slightly worried that the preferred values for the primordial helium are getting closer to 23, whereas the theory would prefer closer to 24. And I would mention, and this is one of the comments I would have here, might involve a research problem for someone, that the dependence of helium, the helium field depends strongly upon the neutron half-life. And that's drifted downward through the years for some odd reason. Most recently from 10.6, 2 sigma down to 10.3. And of course, as you decrease the neutron half-life, the helium goes down. So perhaps the neutron half-life is not bottomed out yet, so to speak. The other issue is an interesting one that might involve a research problem, and that is the finite temperature correction, finite temperature and radiative corrections are fairly important at the time of nucleosynthesis. And for example, they reduce the predicted helium abundance by anywhere between 0.002 and 0.006. And the work that you showed just showed the helium abundance being reduced by 0.003. And this is something that we looked at a number of years ago and perhaps requires even more careful looking at, because the third decimal place is now very significant.
That's true.
And so perhaps somebody should relook at that, and perhaps the effect is closer to 0.006 instead of the 0.003 assumed in the work of Walker et al.
That's correct. Yeah, I agree. That's what I tried to say. Only the helium abundance is still a very unclean problem. And also lithium. I don't know whether I saw Roger raising his hand, maybe he's going to comment. The lithium problem is not yet solved out properly.
Yes, so I have also two brief comments. The first one is perhaps not on lithium, but it is to point out that there is another striking agreement else than the one you have pointed on your diagram. And it is the fact that the value of ISA, which is determined by the consideration of the relative abundance of light elements, agrees within a factor of 3 with the mean density of baryonic visible baryonic matter in the universe. In view of a completely different way of obtaining this number, I consider it as a very remarkable agreement also.
That's what I tried to say.
And the second comment is in fact to follow on your remarks on the uncertainties in the abundance of lithium 7. There are a number of people who have tried to have an initial amount of lithium at 10 to minus 9, but they never have a real plateau. They have a maximum in their predictions between two different processes of destruction of lithium. And I think if you are looking at the dispersion, scatter, and the speed value, it is not true to say that they have, in fact, these predictions, which start from 10 to minus 9, have a very good agreement with observational values. I would concur with Michel, for example, who said that it might be twice the 10 to minus 10, because then the differences are a little bit washed out if you do not start with a factor of 10. But to keep this factor of 10 on 500 degrees is extremely difficult.
No, but I agree with you. The only problem is that if you have 2 or 3 10 to minus 10, then you start to go out from the boxes provided by our colleagues who claim that lithium-7 has to be below 1.4, between 1 and 1.4 to minus 10. So you see, I agree with you that 10 to minus 9 might be much too extreme. And in fact, the plot I showed is showing that the plateau of the lithium abundance in low metallicity stars, for me, is quite appealing for us. But I mean, you have room between 1.4 and 10 to minus 10. You have some rooms, and even 2 or 3 maybe as difficult, at least may put you, especially if you lower the helium abundance, may imply that the baryonic density is very close to the visible ones.
From the Institute of Advanced Research in Grischuk, who will talk on topology of Lizhi.
I'm very invited here to attend to give a lecture in this meeting named Daniel Chalonge. Personally, I'm very far from Daniel Chalonge, but I would say the first time I heard the name of Daniel Chalonge is quite early. It's something like the 1950s. I heard from one of my teachers, Professor Mouette, who is the former director of Beijing Observatory. And in 1930s and 1940s, he was working in France for about 20 years. So he sometimes gives lectures mentioned Daniel Chalonge. And I would again, one of the work done by Professor Chen in France is still close to the topic today. In 1930s, as you know, there are many different models to explain the redshift. One of the models is, you say the photon has some direct mass to explain the redshift. I remember, still today, I still very clearly remember, they say in the 1930s, when they divide of the redshift, then the one of work done by the Professor Chen in France, he showed me a picture published in some magazine in French, astrophysics. he measured the minimum time of the binding. He, as you remember, he showed some these minor minimum time, even the wavelengths of the light. And he found the same in the different wavelengths, give the same the minimum time. This is showing the red mass very low, compared with very low red mass, compared the model of the red mass. I think that's very theoretically very deep integration. I think that's one of the earliest works of particle astrophysics. So this is my personal relation, very direct with Chalonge. Okay, today the topic I will present here is the topology of the universe. That problem also arises quite early. You know, in the beginning of the modern cosmology, that's in the year of 1970, Einstein gave the first cosmological solution from the general relativity. That is starting the cosmology universe. And you know, the geometry is a 3-dimension zero in a 4-dimension space. That's very known. Even at that time, the client already mentioned they have different topology for this solution. They can make a 3-dimension projective space. It means it's identification this point with such point. Then from this becomes a projective space. They also is satisfy the general relativity. So this means the topology problem is coming from the beginning of the modern cosmology. So but this problem has been forgotten for a long time. Even many the textbook always mention, you know, this Vernon mentioned, you know, there are 3 types of solutions of the cosmology from general relativity, the curvature depending on the curvature. You can find many textbooks give a statement. They say the solution of the curvature equal to -1 is space of volume is infinite, and equal to 0 less inverse also infinite. And the plus line is finite. In fact, those statements is true only under the assumption this topology of the universe is a simple connection. In this case, then this statement is true. Otherwise, they can change. For instance, I show very simple example is the so-called 3-dimension torus. You know, this is flat universe, flat space.
So the discussion is open for questions or comments.
What room is there for fractional Euler number?
Sorry?
What room is there for fractional Euler number? Can you consider the possibility?
Which number?
Euler number.
What number?
Euler number.
What? That? Could you repeat?
Yes.
What?
Euler number. I'm thinking of that in terms of.
That's the one you consider the screen. You mean that?
No, I'm considering the possibility of existing global lattice.
Oh, I mean, I understand your question. You're from particle point of view. There are many fields. I know you're from working on particle field. You know, this for the dimension 3-dimension class, you mean many holes, different the oil if we consider the universe flat, then only this line is okay. If you make two holes, it's not the flat universe. You can check. Yeah, only. This is for two dimension very easy. This is one the total. Then make two holes in the order. But that is if we not show the big flat universe, then only one hole is okay. Two holes is the curvature.
Yeah, but that was not even an integer or a number. I mean, it's a possibility of no integer or numbers. I mean, it's folding the space-time, so that affects global density and so on.
No, we only consider flat universe. If we consider curve, we can have lots, yeah, sure. I mentioned there are infinite numbers, sure, that's true. But now we consider a flat universe.
How causality is still valid or could be?
Yes, I want to mention causality even more easy to solve. You know this I not mentioned that because even the early time, this the causality problem is given by the particle horizon and smaller than the observation, but the horizon size with the particle given this one is defined. If the size of the universe the computation is more less than the particles, then it is easy for the causality problem. So you can choose the recombination times of 1,000 given like this. It's just the lower E in our case.
Sure.
Sevre. We have this correlation function between galaxies and galaxy clusters. So,
correlation function.
Yeah.
Correlation function, I think of course in principle you can use that, but the correlation function is useful. It's powerful in the small scale. Now the power spectrum is much powerful for the large scale.
And one more point. You said that the topology of the early universe is preserved. And suppose inflation takes place, how would this affect your... because then we
inflation is... but in doing all the theory, I mean from our observation side, we can theory. Just you can mention the causality. From the small universe to the complete different way one to solve.
I would like to make one more question from you and later. Here you the identification of one in three states. Let us assume that you can make a motivation topology change in the early universe. We don't know about quantum cosmology, but let us think some segment. So there you can also consider identification not only in the 3D space, but in the 4-dimensional space. Mainly if you are looking in terms, for instance, thinking in terms in the Euclidean manifold. And there it could be also a possibility for another topology, because it's just the same thing you are doing, but including the time. You have a non-trivial topology. The new ingredient is that the manifold becomes non-time oriented. There is no global limit of time in that manifold, that non-trivial manifold. But now let's make contact with inflation. If you compute in the way some of the many ways to compute some wave function of the user, if you compute the probability to create or the probability of this configuration, you find that after all, the configuration I am talking about have a higher probability to be realized become the half of the non-trivial one. So that's also, and inflation, is what is called, if you do that with the setter, for instance, or the setter inflation, it was called very, very years ago, without inflation, but playing mathematically by Schrödinger as the elliptic interpretation of the space-time. So that, maybe it's also a possibility that could be introduced in your picture. There are some other comments. If not, I just make a little. Thank you very much.
Okay, it's my very good fortune today to tell you about something which I think is really interesting. And it's interesting for two reasons. First of all, it's very simple. And second of all, it's experimentally testable. And I think those are criteria which are often hard to apply to particle physics theories these days. And the idea is that the baryon asymmetry that we observe in the universe might have been generated in the electroweak phase transition. That only at a temperature of 100 GeV and at an energy scale accessible to laboratory experiments, or will be accessible shortly to laboratory experiments. Of course, the standard explanation for baryogenesis the standard explanation for the last 15 years or so has involved grand unified theories, and that hasn't really worked out. The proton didn't decay, and also much harder to test. So this will be very much simpler, and I think if people had thought of this first, they wouldn't have bothered to try and make baryons with grand unified theories. Okay, so I'll tell you how the Sakharov conditions for producing a baryon asymmetry are met in the electroweak theory, and then I'll try and explain how baryon number violation works by talking about an analog, a simple analog theory. The dynamics are very complicated in the electroweak theory, the full theory. So I'll explain it with an analog theory, tell you how the mechanism works, how you produce an asymmetry, and
thanks to the two fixed fields, you can produce theta field in spot and the CP. Is there any other way to produce a field of this property without two fields?
No, I don't think so. I mean,
Do you
have a drink.
Okay, well, I mean, is there a Nobel theorem? Is there a Nobel theorem or just a
Not that I know of. You can't do it with, you have a single doublet in the standard model, and then you decide what to add.
50 years ago, involving the hydrogen problem, and this puzzle involved both astronomers and physicists, and Daniel Chalonge was key to resolving this puzzle. What I want to talk about now is a puzzle that again involves physicists and astrophysicists, which is yet to be resolved, and that is the nature of the dark matter. One of the simplest questions we can ask about the universe is how much matter is in the universe, and of course the consequences of that question are obvious. It determines the fate of the universe. It's also key to understanding how structure in the universe formed. And the puzzle, as I will describe it, is we now know that most of the matter in the universe is dark. We don't know what its nature is, but if you were to ask what is our best hunch right now, which may not be the correct answer, it is that the dark matter is made of something other than baryons. We believe a working hypothesis is that it's relics left over from the Big Bang. And let's see, Audouze this morning told us about the standard cosmology, and I just want to remind you of two things. First of all, in this model, which is isotropic and homogeneous, the universe just stretches, and its size is described by the cosmic scale factor, which I'll refer to as R. And then there's the equation that governs the evolution of the cosmic scale factor. The expansion rate is just R dot over R squared, and it's driven by the density, and it also depends on the curvature of the spatial hypersurfaces through this term here. And there are three models, as we know. There's the flat model where k is 0, and there's the positively curved model where k is positive, and then the negatively curved model. And so one can relate the curvature to the density of the universe just through the Friedmann equation. So if I just twist this equation around, I see that the curvature term relative to the expansion rate is given by a density over something else that has units of density called the critical density, and that ratio, of course, is omega minus 1. And so if omega is greater than 1, then positive curvature is less than 1 negative curvature, and it's equal to 1 or balance between the two with the flat universe. And I will just quickly summarize our understanding of the hot Big Bang model. Here we are today. Here's the lab scattering surface for the microwave background. Audouze took us to Big Bang nucleosynthesis, and Turok just took us back to the electroweak phase transition, and then there's all kinds of other things going on that we'll hear about.
Right, well, in the last lecture, my He didn't, however, say a great deal about the baryonic dark matter candidates, and that's what I propose to focus on in this lecture. And what I aim to do is, I first want to start off by giving some very general arguments for why we think there may be baryonic dark matter. I'll then discuss the baryonic dark matter candidates. I'll keep that very general, so people who aren't specialists will find it easy to understand. Then I'm going to focus on a number of more specific topics in the baryonic dark matter issue. First of all, the latest developments in cooling flows may be the only place in the universe where we actually have any evidence that dark matter may be forming. I'm going to be talking about gravitational lensing, which will undoubtedly prove the most exciting way of probing the nature of dark matter, and in particular baryonic dark matter, over the next few years. I will talk, if I've got time, about the implications of COBE, which we'll hear from George Smoot about later on, but COBE has interesting implications for the possibility of baryonic dark matter. And then if I have time, I'm going to talk about the dynamical consequences of certain baryonic dark matter models. Well, let me just start off by reminding you of the various dark matter problems that we want to solve, and the associated density parameter, omega, which we have to explain. Now, Michael went through all these, so I will just mention them briefly. If we're looking at ordinary visible galaxies, that's to say, if we're looking on the scale of, say, 10 kiloparsecs, we see that the density parameter is only about 1% critical. There may be dark matter in the disks of galaxies. However, I should stress that the evidence for dark matter in disks is not as strong as it used to be. There is now the possibility that there's what's called a thick disk, which would make the need for dark matter, the 50% dark matter Mike mentioned, go away. However, if it does exist, it will also have a density of something like 1% critical. Now, the density parameter associated with the dark matter in galactic halos, that's very uncertain because it depends exactly how far halos extend. But if, for example, we imagine halos, an average halo for our galaxy, for example, going somewhere between 20 and 200 kiloparsecs, that would correspond to a range of densities between 0.02 and 0.2.
On experimental methods of non-Radial chapter.
Try to locate in the phase space what I will be speaking about. This is a phase space of dark matter. Time to trace the conclusion of Michael Turner is maybe, I would say, our experimentalists are trying to emerge from the botany imposed onto them by the imagination of theorists. So, at the top there you have the dark matter with all its motivations, and there are basically two solutions. Baryonic dark matter, this has been the last talk, where it's unlikely that there is lots in hot gas, but there are experimental tools being put into operation, both for looking for materials and variables, and that has been well covered by Carr. Now, in terms of non-baryonic dark matter, there are lots of possibilities. The most attractive one is that there, as Michael told us, is that there have been exotic particles produced in the Big Bang, and which have somehow survived. And there are basically two kinds of models, the non-thermal models, and the main example are the axions. In spite of Supermike, I will not speak about the axions
like neutrinos of 25 years or so, there are no ideas, actually no good idea how to detect them directly, and therefore I have nothing to talk about on that point. So I will concentrate my talk on the waves. So what I will be trying to tell you is why weakly interacting particles are an interesting case, then review rapidly the accomplishment of a third generation of detectors, and tell you there is a basic conclusion, which is that with existing technology, it's very difficult to detect dark matter winds at the level of what is expected film theory, and therefore that we have to develop new technology. I will give you an idea of how far we have got, which is actually further than I was expecting a few years ago, and at the point when we can really start to think about pilot experiments. And if I have time, I will speak a little bit about phonons of equilibrium. So,
the journey of today is devoted to different aspects of the cosmic microwave background radiation. The first talk is given by Professor from the University of California, Berkeley, given us an overview.
Well, I would like to thank Norma Sanchez and for the honor of coming here to help inaugurate this new School of Astro-Fundamental Particle Physics in honor of Daniel Chalonge. My talk is going to be about the cosmic microwave background, and these are the topics I'm going to cover. George Smoot is going to go into some details on the spectrum. I will talk briefly about that. I will spend most of my talk discussing the anisotropy of the cosmic microwave background and the implications for large-scale structure. Okay, so let me begin with some remarks, then brief remarks about the spectrum. The COBE and at the same time a rocket flight by Grischuk and collaborators established the Planck spectrum with remarkable accuracy, and the newest result that you'll hear about is something like there are no deviations to within 40% feet from the Planck spectrum. This has to be one of the most remarkable verifications of the Big Bang cosmology, it seems to me. Now, I want just to mention one or two of the implications of this. In the standard Friedmann cosmology, you can ask the question, when was the black body photons created? When were they thermalized? You have to go to an epoch in the universe when the density was large enough to absorb and re-emit photons. And this is long before the last scattering occurred of the photons. In fact, it's roughly 1 year after the Big Bang. So when we study the Planck spectrum of the microwave background, we're probing the universe to within about a year of the Big Bang. And it's the most direct experimental probe of the early universe. More direct, actually, than nucleosynthesis, which is somewhat, more, I think, more rapid and interpreted.
Next talk is given by Prof. from Majorana Laboratories, COBE and the spectrum and anisotropy of the microwave background radiation.
We want to thank Norma and the other colleagues from the Majorana School for inviting this school, and particularly for letting us split the talks up. And so I will talk about the anisotropy, and Al Koga will talk about the spectrum this afternoon. He will cover fire-active bolts and the other experiments of the rocket experiment of Bush et al. And an experiment that our group has done, and in addition other measurements. And I will talk about the anisotropy, and because there are other talks, particularly Paul Richards, I'm mostly going to focus on Kobe and talk about the Derby and the DMR instrument. And so to tell you about it, I'll start with, here's what the Kobe spacecraft looks like. This is a drawing, sketch, an artist's conception of what the satellite looks like, with the various parts labeled. You can see there are 3 experiments on board the satellite, and so I'll talk about the results from 2 of the experiments, and I'll talk about the 3rd. It wouldn't be an experimental talk if I didn't show you a picture of hardware. So on this side is the spacecraft that was getting prepared to go on the rocket. The top is the solar shield that you see at the top. Keeps us protected from solar radiation and earth radiation, and keeps the instruments cool. The lower part of the solar cells that you see around, the people in there give you scale of what the satellite looks like. All this was put on top of an Delta rocket, launched in November 1989, and so you get a feel for it. There are 3 instruments. 2 of them are liquid helium-cooled Dewar. It's a superfluid helium Dewar that lets the detectors be at 1.8 Kelvin, and we can control their temperatures. The 3rd instrument, which I happen to think is the best because it's mine, is on the outside. It's a 3DMR radiometers, they're differential microwave radiometers for measuring the anisotropy of a microwave background. So let me tell you a little bit about what our original motivation was, and that was to try and do cosmology. This satellite, the first satellite that NASA has to do cosmology, and of course we're sort of astronomically oriented, we're using photons. So here's a paper that Mike Turner's an author on, I believe. This is the grain-defined photon spectrum. That is essentially all the photon coming from the universe to us today, starting from the radio up into the very high energy gamma rays. And this is the diffuse background spectrum of the universe. This is the foreground galaxy and other sources taken out. And you can see that there's the radio sources, which look very much like the drawing that Joe showed you of synchrotron radiation from the galaxy. There's the microwave background. There's an IR background, we believe. Actually, at this point, they're all on the limit. So as we can see, there's the optics where we look with our eye, pictures of what's going on. And then the ultraviolet, which little is known about. The X-rays, which has a well-known background. And finally, the gamma rays, which is pretty well undetermined. And what we did was look at this, have a picture of the site. Where can we do the best?
The third lecture this afternoon is the inflationary paradigm today, and it's by Michel.
This one. So what I would like to do is focus, when talking about inflation, focus on the big picture, the grand themes, and in the process talk about the evolution of inflation from old inflation to new inflation, and then I want to spend a lot of time on the newest model of inflation, which I think is quite promising. While doing that, I want to talk about the origin of density perturbations, which are so important for the formation of structure, and also talk about the gravitational waves, because this is one potential way of verifying inflation. And then I'll spend And in terms of talking about the newest model of inflation, it involves an inflationary transition that is more like Audouze's original idea, where the phase transition completes with bubble nucleation. And so since this is the key to understanding the newest model of inflation, I want to spend some time talking about bubble nucleation, which is also of relevance to other phase transitions, perhaps even the phase transition that Neil Turok is interested in. And then last but not least, inflation is a very, very beautiful theory, but in science, being beautiful is not enough. We have to test our ideas. And so a key in inflation is testing the inflationary paradigm. Let me first display my license to talk about inflation, so that this qualifies me to talk about inflation. Thank you. Okay, the big picture. What does inflation promise to do for us? It addresses a number of shortcomings, and by shortcomings I don't mean logical inconsistencies, but loose ends of the standard cosmology. And they are known as, I'll describe them as the horizon and flatness problems and the monopole problem. In addition, as has probably become very clear, inflation has the possibility of providing a blueprint for structure formation, providing the initial data that are necessary to study the formation of structure. Density perturbations, inflation unequivocally predicts that we live in a flat universe, which means that most of the matter in the universe is something other than baryons. And this, of course, has implications for the microwave background. And, of course, this blueprint, I think we will see, and we've already seen, that this blueprint is really a crucial feature of inflation because it's led to the most detailed scenario for structure formation ever, so-called cold dark matter, a scenario that's so detailed that it can be falsified. And so we now have great debates about, well, is cold dark matter ruled in or ruled out? And these great debates really don't take place about other models of structure formation because they're not detailed enough.
For the University of California, Berkeley, millimeter wave measurement of CDR on intermediate scale.
First, let me say how delighted I am to be invited to Ricci and listen to the fabulously powerful theoretical minds that are here. My talk will be strictly about experiments, and it will be about small science experiments, and it is measurements of the anisotropy, the cosmic microwave background on intermediate angular scales. And I'll first talk about, say, an experiment going on at Berkeley at UC Santa Barbara, which we call the millimeter wave anisotropy experiment MAX. It's part of the the program in the Center for Particle Astrophysics. And then at the end of my talk, I will talk about CERTA, the Space Infrared Telescope Facility, which has some capabilities for doing this kind of science, which are not widely recognized. Now, to show how a small science program grows into a slightly less small science program, I've made a diagram here, which isn't as elegant as Mark Turner's, but almost as complicated. There have been programs at Berkeley, NASA balloon work on the spectrum of the microwave background, work on the detectors for the Japanese infrared telescope in space, work on detectors for CERTA, and all of this is fed into a capability for making volumetric detector systems at Berkeley. At the same time, in Phil Lubin's group at Santa Barbara, there has been a NASA-supported ballooning activity, SIS quasi-particle heterodyne mixers, observations from the South Pole, and this has developed a capability for balloon telescope and coherent receivers, which are now moving over to high electromobility devices. And this has merged into the MAX experiment and into a larger program funded substantially by the Center for Particle Astrophysics, and it is a multi-spectrum number of people are involved here, Berkeley people, Santa Barbara people, people elsewhere. But I would say that relatively few of these people are full-time, and so this does qualify as small science, and it satisfies, I think, what I call the 1% theorem, and that is that projects of this kind cost about 1% of what a major space program costs. That's not an accurate number. It's about as accurate as any number is calculated in cosmology. But these programs satisfy or are responsible for some very, very important things. In particular, technology development, how you do experiments, and training of people, and then they do produce data, but not on the scale of Kobe, as they never could with the sort of level of the activity.
Good morning. Given by Professor Sevre from Imperial College at London on cosmic extremes, Carr and time.
Right, so let me start by trying to explain what cosmic strings are. The simplest model in which cosmic strings appear is the relativistic version of the Landau-Ginzburg model, otherwise known as the Higgs model, which is a model of a single complex scalar field coupled to a gauge field. The Lagrangian is written there. This is the Lagrangian. D mu phi is the covariant derivative of phi. And F mu nu, of course, is d mu a nu minus d mu a nu. The important thing is the potential. This potential is chosen to be, first of all, symmetrical under phase rotations, don't depend on the modulus of phi, but also it's chosen to have this form, the Mexican hat shape, which has a maximum at phi equals 0 and a minimum at some other value. So the minimum is actually around the circle. The phase angle is arbitrary. The theory is gauge invariant, of course. It's invariant under the usual gauge transformations. And the important thing is that there is a degenerate vacuum state. The ground state of the potential is degenerate. And in such a theory, there is, in general, a phase transition. If you go to very high temperatures, where the thermal fluctuations are large, phi will be fluctuating wildly, and the average of phi will tend to be zero. But when the temperature falls, phi tends to settle down into the minimum at some point in the minimum, and so at the lower temperature the symmetry is broken, phi tends to sit somewhere around the minimum. So you have this phase transition. And if the universe undergoes such a phase transition, I should say there are many theories that use structures of this kind. If the universe undergoes such a phase transition, then as it cools, the field phi will acquire a non-zero expectation value, and once you get well below the critical temperature, phi will settle down to the minimum potential, but the angle will be arbitrary. And of course, in widely separated parts of the universe, it will tend to vary. And so the phase will vary from point to point. And you can then
So I'm going to tell you about a new mechanism for generating structure in the universe, either with or without inflation. Personally, I regard inflation at the moment as a brilliant idea without a good realization in any specific model. And for that reason, I think it's very interesting to think of other ways of making structure. And at this stage, I'm perfectly willing to assume the universe began flat, homogeneous, isotropic, in thermal equilibrium, and ask yourself if from such a simple beginning is it possible to generate large-scale structure. And this is the mechanism which can do it. There's no fine-tuning in this mechanism required, unlike inflation. Delta rho over rho comes out to be the symmetry breaking scale over the Planck mass squared, which is about 10⁻⁶ if symmetry breaking scale is the gut scale. And so that's also nice that we have an indication from low energy physics that there is some scale around the unification mass. And so one feels a little happier working on something for which there is at least some evidence from low energy physics, rather than some Higgs coupling parameter, lambda, which you have to dial to very small values, as in many theories of inflation. Texture arises automatically in many extensions of the standard model. In fact, it's one of the only mechanisms for which the mechanism arises in theories that were not invented in order to make the mechanism work. I don't think there's any theory where inflation arises in a theory that works, in a theory which wasn't invented to make inflation work. That's not the case with texture. Family symmetry schemes and technicolor schemes invented long before texture was understood actually produce it automatically. It has, I think one of the most interesting things is that there's completely different physics involved to the physics of inflation. That the way you make fluctuations is entirely different. It's essentially classical physics and much simpler in many ways than the physics that goes into the quantum fluctuations in inflation. So it's totally different physics. But it ends up with a very similar phenomenology to the quantum fluctuations in inflation. The power spectrum is actually almost identical, and many of the features, many of the success makes high-density regions around the defects, which leads to galaxy and crater formation at very high redshift, not low redshift, and it has slightly more large-scale power than inflation. The great virtue of it compared to cosmic strings, which Tom Kibble just talked about, is that it's much easier to do calculations with it. And in the year and a half that this theory has been around, we've taken it really a lot further than cosmic strings have been taken. And I would say certainly much remains to be done. But for example, careful calculation of the temperature isotropy.
Institute of Moscow, the qualitative cosmology.
Yes, may also explain to you that you have not to be worried about the time, because I am intending to finish at 1 o'clock, or you will have time for discussion. Okay. Not long ago, I met Richard Arnold, everybody knows his name, and showed him one picture, which I am intending to show you. On the top, okay, first. Okay, I showed him this picture which you see in the corner of the figure, in the right corner, and asked him whether he recognized the meaning of this picture. And he was not able to recognize. And when Norma Sanchez invited me to give a lecture at this school, I decided that there is a reason to present this approach to the classical cosmology. If Dick Arnold does not recognize this picture, then it's a reason to give explanation and this approach at the school. The idea is very simple, and we, at least in our Moscow school with our colleagues, and quite often use the method of qualitative theory of dynamical systems to study different problems in cosmology. In some sense, the universe is a dynamical system because it's described by some differential equations, especially in the case of homogeneous universe. The homogeneous universe can be described by differential equations, these derivatives with respect to time, different orders of derivatives, but for such non-linear equations we know the method, how to investigate. And quite often we are not able to find the exact solutions, but the qualitative method of investigation of dynamical systems gives us the possibility to analyze all possible types of solutions. Therefore, the purpose of this lecture is very simple, to give an introduction to the cosmology as a dynamical system. Therefore, I will analyze very simple classical cosmology and very simple cases of homogeneous spaces. I will start with the type 1 Bianchi, according to Bianchi classification. This is the simplest homogeneous homogeneous universe, and then I will also describe all the possible Friedman models, which they are represented by different, they belong to different types of Bianchi classification, and then show some remarks how the influence of dissipative processes change this picture. Okay, let's start now with the simplest cosmology of first Bianchi type. because it corresponds to abelian group of motion, which is simplest group, and the space-time metric can be represented in such form where we have three scale factors, R1, R2, R3, functions of time. This is the simplest geometry. And now we have to write the Einstein equation for this system, for this metric, and in the right side of Einstein equation we have to write the energy momentum tensor, which we always take in the form of hydrodynamic form. Then we need equation of state for generality. Equation of state is the pressure as a function of the energy density, and therefore the Einstein equations can be written in standard form. It's a Lizhi tensor, energy momentum tensor, and we also introduce cosmological term for generality, and it gives you the rich picture, a richer picture at least. Then, of course, for simplicity, this is also the standard method. We introduce commutative different system. In commutative different systems, the component of the velocity are very simple. And now the problem is, which we have to solve, is to find the scale factors and the energy density as the functions of the temperature, evolution of the universe. It is convenient to introduce a Hubble function, which is we introduce the product of the scale factors, which defines the volume of the universe, then the logarithmic time derivative of this new function R, we call Hubble function. And it is very convenient because the equations can be written in very simple form after we introduce this Hubble function.
Good morning. I am pleased to announce the first lecture of this morning given by Erice-Centro from the Observatoire de Cayrel on transport problems inside the stars.
This lecture is conceived as far as a course on an introduction to the problem of transport processes, so that I have first to present formally what is the importance of the young constitution of the stars in astrophysics in connection with other problems, especially as a large part of this course has been devoted to cosmological problems. I remind you that stellar ages gave the cosmic clock through the age of clusters, and indeed also to very important results concerning the dynamics of the galaxy, with the motion of stars depending on their age and chemical position, which is a strange thing. The chemical position of the stars is derived naturally first from the spectroscopic data, but there is a question of the meaning of the spectroscopic data, which means that one has to take into account the transport processes, and especially in the case of nuclearly processed elements, and lithium in this special case. And it has been mentioned, I understand here, that the concentration of lithium, of primordial lithium, is a very important quantity about the problem of the origin of the elements, and this is one of the problems I shall talk about. And finally, there is an important question concerning the conservation of angular momentum and the transport and exchange and loss of angular momentum
for which we have now, during the recent years, obtained very important results coming from radioseismology, and there are now plans about asteroseismology, but it will come in the future. So we have then to get into one of the aspects of this problems of Indian constitution, which concerns the transport processes. We know of three possible processes for the transport of scalar or vectoral quantities. This is the advection by large macroscopic motion. There is the process of microscopic diffusion, which is well known in kinetic theory of gases. And there is also random macroscopic processes, the typical one being transport by turbulence. The consequences of this effect is that the classical models of the internal constitution of the stars, without any transport of chemical elements, has to be reconsidered. It has effect on structure. The chemical composition is not directly the one which derives from the destruction of elements or production of elements by nuclear processes. This has effect on stellar evolution. One has to derive from the surface abundance the internal properties, or conversely, trying to understand anomalies in the surface abundance. This has effect on the neutrino flux, and unfortunately, the situation at that point is not very well developed, but I shall mention the possible importance of it. And finally, in the interpretation of this seismological data, it is extremely interesting. The test of the transport processes which we shall consider are the lithium elements, the internal rotation of the sun, and the neutrino flux. It depends only on the distribution of the energy spectrum of the droplet flow, and this could exist even in non-rotating stars, because it is due to waves which are produced by the absorbent flow in the convective zone. It is only in the case when you consider the angular momentum transport that you have to take into account the surface value of the angular velocity, because angular momentum is carried at that frequency from the star.
Biggest storm.
What's the
He will talk on general relativity, a cornerstone of 20th century physics.
But there is first of all, let me thank Sanchez for the flattering introduction, and let me report one experimental finding that's very obvious, and that is that as this meeting is approaching its end, more and more speakers are holding on to the suggested 50 minutes, and so I think it's beaten everybody by talking only for 35 minutes. I think I should report the facts without attempting to interpret them. But I will try at least to follow the suggested 15-minute duration. What I had originally thought when Norma Sanchez invited me to talk here, that I would meet a group of people for whom general relativity was something that they had to pass an examination as graduate students, and then having to work at this obviously was okay, thanks a lot. And I will probably more successfully wired north south. And as I found out simply by listening to the talk that this was a total misconception. I think what I will try to do is to de-emphasize the aspects that were intended for those who had tried to get all they ever learned of relativity by and emphasizing this was the intended outline of my talk. What I wanted to try and what I will try to concentrate on is to discuss the conceptual contributions rather than the formal contributions that general relativity has made to the structure of current physics, and perhaps to discuss the unresolved problems that exist, particularly in attempting to fuse the two principal branches of theoretical physics of our time, that is to say, quantum theory and general relativity. I will not, because there's simply no time for that, I will not go into the program of unified field theories and motivation for that. I'm very aware of the fact that any physical theory, including general relativity, is likely to have a finite lifetime. And in fact, if I may quote my revered teacher, Einstein, he used to say, Newton lasted for 300 years. If general relativity lasts for 50 years, I could be very pleased. As a matter of fact, the 50 years have long been up, and general relativity is still very small.
Can you elaborate some more on prospects for a unitary theory?
Well, let me put it this way, that this is a personal opinion. Since I suspect that the further development of general relativity made above all of our reliance on manifolds. Historically, what used to be called unitary field theory or unified field theories were based on manifolds, 4-dimensional, 5-dimensional, 6-dimensional, and so forth, but always manifolds. So it seems to me, I don't know what to put in the place of the manifold. Perhaps some kind of a lattice in the mathematical sense. That is not a raging lattice, but something in which the open sets of ordinary topology are replaced by different structures which do not obey the two distributive laws but replaced by distributive inequalities. That's what's called a skew lattice. But this is really a very wild conjecture which I would not urge anybody to try to elaborate unless he or she himself thinks that that's the way to go. I mean, it's clear today that to go from the gut end is going to be very difficult because with general relativity go from Poincaré invariant theories to general relativistic theories. So my tendency would be to say let's approach it from the other end. But these are merely guesses and I don't want to claim that that's necessarily true.
You have mentioned about Einstein's words. He said that he would be happy if general relativity was valid for 50 years. I wonder if this is the same occasion where he mentioned 50 years in different contexts. I was quoting him once as saying that special relativity and other his contributions could have been done by other people because they were in the mainstream of physics of that time. But for general relativity he was making an exception, and he seemingly was saying that but for general relativity it would probably take 50 years if it was somebody else, not me, constructing general relativity. So what I'm wondering, whether it is a result of all these translations from German to English and Russian, or is it two different occasions that you mentioned 50 years?
I think the statement you called was a public statement. I would have taken another, if it had not been for my work, would have taken another 50 years to produce general relativity. That was a public statement. What I reported was a very private statement, a private conversation. I think it represented Einstein's thought, but he didn't, as far as I know, they might say it publicly. As far as translation is concerned, let me assure you that while I was at Princeton, Einstein, Bach, and I talked to each other in German. There was no translation back and forth. And Nathan Rosen was my predecessor in Princeton, told me that he had to learn German in order to work with Einstein.
You're looking at me, but I didn't ask the question.
I didn't know whose voice it was. I thought it was yours. I see. Okay. Good enough.
Concerning quantization of general relativity, quantization of gravity, you did a lot of overcoming at your time, many difficulties, and dealing with the Hamiltonian approach, which gave the basis to what we know now, for instance, Wheeler-DeWitt equation, wave function of the universe. We were basically written down in little progress, I mean, from the point of view of fundamentals, have been performed. And in the prospect you presented us, for instance, quantum cosmology or quantum dealing with the unification of quantum theory and general relativity. I would like to add, the possibility that appears now with the string theory, because any of the approaches, Hamiltonian, Spati integral, whatever for quantization, any of the many different frameworks we deal with the variables in general relativity, all that is in the framework of point particle field theory, and we don't know how to deal in the approach of point particle field theory a consistent theory of gravity. So I found that a formidable task for our generation is to try to go beyond point particle field theory and to try to check if the possibility of the string theory could be successful or not, but to try to go beyond that.
I think there are a number of people who believe they have solved the problem. This is what is known as the theory of everything. I must admit that I'm a skeptic and don't believe it. I have the feeling, Norma, that there's something very fundamental that you simply have not grasped, that none of us have grasped. And although it's certainly sensible to try everything that may occur to somebody, be it strings or superstrings, supersymmetric theories, and what have I think that if you look at all physics journals, you discover that a lot of people have tried lots of things that history shows didn't work. And I'm sure that 99% of what we are doing now won't work. We just don't know which is 1% that might work. This may sound pessimistic, but I'm not pessimistic. I think that 20 or 30 years from now, we will understand many things that we do not understand now. I don't believe that we will ever in the history of mankind have a theory of everything.
I certainly agree that the main theory of everything is too ambitious, and certainly has proven, all the excitement and the 80s and 84, people started to call it, to speak about the theory of everything. Certainly, I think that we cannot still call that theory of everything, but it's the possibility we have now at hand to explore and to check if could be somewhere to go for theory of everything.
Maybe I should elaborate on one point that I cut short because I was afraid of running out of time. If you ask what is the form of a generator of an infinitesimal coordinate transformation, that turns out to be integral of the form is this Majorana? Yeah. three-dimensional integral was Cauchy surface multiplied by the four constraints, or by a linear combination of the four constraints multiplied by arbitrary coefficients, u, alpha. I'm using alpha just to sum up the four constraints. Now, supposing you say the simplest form is that the new alphas are functions of the coordinates only. That is, that they do not depend on the dynamical variables. It turns out if you try to build up the Lie algebra, that is, you take two such things. The tilde is equal to another thing. Here we have a different set of coefficients. You tilde alpha. You form a Poisson bracket, or the commutator between the two generators G and G tilde. It turns out that the Poisson bracket will have that form again, very nice, but the commutator coefficients will not be pure numbers fields, even though the original use may be. So in order to close the Lie algebra, you have to consider coefficients of all dynamical functions. Now what does that mean? It means that if this is your Cauchy surface, and you take a point here on the Cauchy surface, you move it to an infinitesimal neighboring. As long as the mu's are purely numerical, that vector is independent of the vector. But if mu itself is a function or functional of the dynamical variables, it means that with different Cauchy data, that point may get mapped on all kinds of points. In other words, you no longer have a mapping of point on point, but you might see the mapping of decorated points on decorated point. And you mean by decoration all the dynamical variables and their derivatives at the point of your point. But a better way of looking at it, at least I think a better way of looking at it, is to say, supposing that I have a bunch of functions here, that is a particular set of field values, it gets mapped on each such set of field values gets mapped on the set of field values, and you don't need the decorations anymore. And this is what originally made me feel that perhaps the world point was on the way out, without trying to burst the formal framework of the theory.
No more questions or comments. From CERN at Geneva and director of the Center Ettore Majorana, who will talk on the future of high energy physics. Thank you.
Before starting the lecture, I'd like to read two messages arrived just a few minutes ago. I will show them, they are in Italian. One is from His Holiness the Pope, and the other one is from the Prime Minister of Italy. I will read them in Italian and will translate later. La presenza in esce di illustri astrofisici per onorare la memoria del professor Chalonge, fondatore della scuola astrofisica francese, cui viene oggi dedicata la prestigiosa scuola di astrofisica del centro di Erice, mi è occasione propizia per auspicare che nella nuova era di pace e di solidarietà tra i popoli l'uomo possa sempre più dedicare la sua intelligenza a studiare il creato, seguendo il grande insegnamento di Cayrel, di cui si celebra il quarto centenario, mentre di cuore invoco la benedizione divina su tutti i presenti. Giovanni Paolo II. Il Prime Minister says, in occasione di inaugurazione Scuola Internazionale Astrofisica dedicata al grande scienziato Chalonge, precursore della spettroscopia stellare e ideatore di nuovi strumenti per l'astrofisica moderna, desidero fare pervenire i miei più vivi auguri per lo sviluppo della importante iniziativa scientifica. Mi compiaccio inoltre che il dono da parte del governo francese al Museo della Città della Scienza di Erice dei prestigiosi strumenti inventati e realizzati da Chalonge, che costituisce un gesto di grande valore per l'amicizia tra la Francia e l'Italia. Giulio Andreotti. These messages will be translated, and now I start my lecture by first thanking Norma Sanchez for the organization of this extremely interesting school and for the presence here of Cayrel Chalonge, to whom I am bound by all friendship and affection. Ma io questa fare prima ero finito per terra. This is a new invention by Norma Sanchez of the state transcription. So the future of energy physics can be synthesized in one graph. Of course, this is my view of the future of energy physics. And I will try to justify in the course of this lecture why this is correct. I just would like to call your attention to the fact that our physics is in this range at present here, which is 100 GeV. And then you will see what is the meaning. I will explain to you what is the meaning of these various drawings, lines, and all this. Let me just tell you this is the number of families, the number of Higgs, the level where supersymmetry is supposed to be broken, the short-cutting constant at the Z0 mass, which appears to be 0.118, and the mixing of the electroweak interactions, which turns out to be 0.2334. These are the basic ingredients for the existence of these lines, which is the result of a very recent work of myself and my collaborators. And these are the two projects which are supposed to give important contributions into the development of our understanding in the field of nuclear physics.
know E plus C minus physics. Now, when hadronic machines were very popular, I was working in E plus C minus physics. So I've been working with all machines. Now the game is the following now. It is true that E plus C minus machines provide clean events, so to say, because I could show you the events we have taken with L3, they are very complicated. Nevertheless, they are coming from 2 point-like particles. But the question is, if you work at 1 TeV and no one knows how to build 1 TeV machine, even Bart Richter, he has no idea how to build such a machine. Even if he knew how to build 1 TeV machine, if supersymmetry breaking is going to take place at this level here, he will not discover anything, because this is threshold. It has nothing to do. So, let me repeat. The new point is now to know where God has fixed the energy where supersymmetric particles will be